Welcome everyone. Engineers are often interested in calculating the stresses developed in the structure to evaluate the design. However, there are situations where artificially high stresses develop, so this poses a big challenge. Understanding situations where artificially high stresses arrive and addressing them is the focus of this lesson. We will discuss situations such as point loads and constraints, re-entrant corners, contact with sharp corners, and over-constraints. This video will consist of a short lecture followed by a walkthrough example using Ansys Mechanical. Ready? Let's get started. To properly use finite element results in stress analysis, one must be able to identify and address situations where artificially high stresses may develop. In many cases, these artificially high stresses will grow without bounds as the mesh is refined. These can lead to confusion as to what is the result that should be reported. Knowing what can be done about the artificially high stress will be a learning outcome from this video. Let's investigate when and why these occur, but first recall that in structural finite element analysis, we're directly solving for the displacements and rotations at each node. These are the unknowns from the global matrix equations. These quantities will always converge to a unique solution as the mesh is refined. The stresses and strains, on the other hand, are derived and they're not calculated directly from the global matrix equations, so their values may not converge to a unique solution with a finer mesh. First, let's summarize the most common cases for artificially high stresses, then we'll look at each one in a bit more detail. Applications of loads or constraints on a single vertex or node, re-entrant or sharp corners or edges, contact with sharp corners or edges, and over-constraints due to improper boundary conditions. These are not all inclusive, so again, there may be other reasons for artificially high stresses, but these are the most common. For point loads and constraints, applying a force or constraint to a single vertex or node will create a situation where, as the mesh gets finer, the stress will increase. Notice how we have artificially high stress that grows as the mesh density increases. This arises because every node has an associated area of the mesh. In the simple equation of stress equals force over area, as the area gets smaller with mesh refinement, the stress increases. Similarly, if we constrain a vertex or single node, the reaction force at the constraint will also show similar behavior. So how do we prevent this? For solid and surface geometries, apply the constraints over lines or areas. In these cases, as the mesh is refined, the total area the load is applied over does not reduce, and hence the stress does not increase without bounds. Now, there are times we may use a constraint on a vertex, such as when we wish to apply minimal constraints to a body just to hold it from moving, as in the case of free thermal expansion or inertial relief. In these cases, there are only very tiny forces that arise to prevent rigid body motion, and applying the constraints to the vertices or nodes is acceptable. Also, applying a force or constraint on a vertex of a line body does not show this behavior, so there is no reason to avoid these situations. For the next case of artificially high stresses at re-entrant corners or edges, this comes up quite frequently in finite element analysis. A sharp corner without a fillet will be the source of a stress singularity. As the mesh size is reduced, the strains and stresses in the sharp corner will tend towards infinity. Typically, we may deliberately leave out the small fillets as they tend to drive the mesh size smaller and hence create more computationally expensive models. But then, we must understand how to deal with the artificially high stresses they create. So how do we address these singularities? We have some options. From St. Venant's principle, we know that the influence of the singularity is local, so the stress away from the singularity are still valid, and of course, the displacements and rotations are still valid. In this case, we can scope our results so as to not include the location of the stress singularity if it is not a region of interest. If we are interested in the region, we should add in the fillets, so the mesh no longer has a sharp corner. In this case, the stress will no longer be singular. You may need to have small elements to resolve the curvature of the small fillets, but you'll find that the stress converges with mesh refinement. It's also worth noting that stress risers, such as those at small features like fillets or holes, may have high stresses that in a linear analysis will exceed the yield stress of the material. Knowing the stress has exceeded yield may be enough for the engineer to consider a design change to reduce the stress if yielding is not desired or permitted. Alternatively, if yielding is permissible, a plasticity material model can be included in the material definition to compute the extent to the plastic region and associated plastic strains. Another situation where we have artificially high stresses is with contact, like having a point load. When the contact force gets concentrated to the vertex or edge, the force is localized, and as the mesh size reduces, the area associated with the nodes in contact decreases, causing the stress to increase. In these cases, adding in a fillet or chamfer is a common fix to eliminate the artificially high stress. The last case that we'll discuss is the artificially high stress we see with improper boundary conditions. It's important to specify boundary conditions that accurately represent the model's interaction with the rest of the world. A common mistake is that we choose the geometry to model, then we think all the parts that are interacting or connected to our geometry can always be represented with the boundary condition. This is not good practice. Instead, we should think of it the other way. What does a boundary condition represent? And are all the other parts or components not modeled with geometry behaving like the boundary condition or load? For example, take this dog bone tensile test specimen. It's convenient to specify a fixed support where the grips hold the specimen. But is this an accurate representation of the boundary? The grips are not welded to the specimen, so by using a fixed support, we are restricting straining in the lateral and thickness direction from the Poisson's effect. Notice this gives rise to artificially high stresses near the boundary condition. Now, to get around this, you could leave the fixed support as is and scope the results to only the region of interest and ignore the stresses near the fixed supports. On the other hand, we can model the clamping of the grips with frictional contact, and now we are not restricting the Poisson's effect. This results in no artificially high stresses developing, and the peak stresses are where we expect them to be. Now, in addition to the Poisson's effect, another situation where improper boundary conditions are an issue is a case of over-constraint with thermal expansion. Take the circuit board where the mounting holes are fixed supports. Solving for the thermal stresses, we see artificially high stresses in the mounting holes. In an actual design, the boundary condition at the holes is not fixed or rigid. There may be designed clearances, grommets, or standoffs to allow for flexibility to accommodate thermal expansion, and the other bodies, including standoffs, would also be undergoing thermal expansion. If the part is truly free with no supports, then applying just the minimal amount of constraints to prevent rigid body motion while not restricting thermal expansion. Checking your reaction forces in these cases will help you verify that the boundary conditions are not over-constraining the model. Finally, when evaluating stress results, take care to understand the difference between a stress singularity, such as the case we discussed with re-entrant corner, and a stress riser, also known as a stress concentration. Stresses that look artificially high may be legitimate, so spending time to understand and doing a mesh convergence study is recommended. Stress risers such as a hole in the plate or a fillet on a step shaft, just to provide two examples, will have larger but finite stress. These may even have a closed-form mathematical solution and should not be ignored as artificial or artifacts of the model. Now let's see how to resolve the artificially high stress in a walkthrough example in Ansys Mechanical. The example shows a half-symmetry steel hook that's attached to the wall by a screw and exposed to the force at the hook's tip application. This example will address problems such as re-entrant corners, point loads, and constraints that can cause artificially high stresses in the model. In addition, we'll show the ways to improve the model by better preparing the geometry and applying proper loads and boundary conditions. Let's get started. Go to the project page and insert Static Structural System. Rename the System A to Original. Right mouse click on Geometry and import Geometry. Browse for the file hook.scdoc. Double-click on the model to open Mechanical. Click on Home tab, Units. Set units to millimeter, kilogram, newton, second. Expand Geometry. Click on the hook part. The material assignment is structural steel and we will leave it as is. Expand Coordinate Systems. The coordinate system plane 10 is created in SpaceClaim and it will be used as the symmetry plane. Expand Symmetry. Click on the Symmetry region. In the Details view of the Symmetry region, the symmetry plane is set to XY plane of plane 10 coordinate system with the symmetry normal set to the z-axis. Highlight Mesh, set element size to 1 millimeter. This is a global mesh control that will affect the entire model. Right mouse click on Mesh and insert sizing. This is a local mesh control that will affect only selected geometry. In this case, we would like to get finer mesh on the selected faces. Click on the face, Selection Filter. Select these three faces, sharp corner, and the tip of the hook, and apply a scoping to the face sizing. Set element size to 0.5 millimeters. Right mouse click on Mesh and insert sizing. Now we're going to specify element size on the back edge of the hook. Click on Edge Selection Filter. Select the back edge and apply as geometry scoping under sizing. Specify 0.5 millimeter as the element size. Right mouse click on Mesh, Generate Mesh. Next, we're going to define loads and boundary conditions. Right mouse click on Static Structural, insert Fixed Support. Note that this fixed support will cause over-constraint of the model because the hook is not truly fixed at this boundary. It is connected to a deformable wall using a screw. One of the common mistakes when defining boundary conditions is the overuse of fixed supports. Select Face Selection Filter and select these three faces. Apply as a geometry scoping for the fixed support. Next, we're going to apply a point force. This is also one of the common mistakes, where the load is applied to a vertex instead of being distributed over an edge or area. Right mouse click on Static Structural and insert Force. Select Vertex Selection Filter. In this case, we'll apply the force to only one vertex. Select the middle point on the tip of the hook and apply. Set Defined by Components. Set -35 newtons in the Y direction. Let's solve the model. Right mouse click on Solution, Solve the model. Now we will post-process the results. Right mouse click on Solution, Insert Stress Equivalent Stress. Right mouse click and evaluate all results. Highlight equivalent stress. Notice how the mesh is plotted over the results. If you want to show the results without the mesh, click on the Results tab, expand Edges, select No Wireframe. In this example, we would like to visualize the mesh over the results so we can easily see if there is a high stress at the single node. Click on Minimum and Maximum Probes. If we zoom into the areas of maximum stress, notice how the stress is high at the location of the point load. This is the artificially high stress or stress singularity caused by applying the force to the single node. Recall from the lecture that every node has an associated area of the mesh, as the stress is equal to the force over the area. So if we would continue to refine the mesh, the stress would rise and eventually go to infinity. Let's now check the total deformation. Click on Solution in the tree. Click on Body Selection Filter. Select the whole body. Right mouse click, Insert Deformation Total. Right mouse click, Evaluate all results. It's always good practice to check total deformation and make sure it is as expected. Let's now scope equivalent stress to a few critical locations in the model and examine the stress values. Click on the solution in the tree. Click on the face selection filter. Select this face. Recall that the point load was applied to one vertex in the middle of the top face. Right mouse click and insert stress equivalent stress. Right mouse click, evaluate all results. Zoom in the area of max stress. Notice how the stress is high only at the point load location. This is artificially high stress. Click on the solution in the tree. Click on face selection filter. If we're interested in getting stresses away from the artificially high stress location, we can scope stress to the geometry of interest as shown here. So the stress singularity at the point load location doesn't affect the stress on the vertical face of the hook. Select the vertical face as shown, right mouse click, insert stress equivalent stress. Right mouse click, evaluate all results. You can see how the maximum stress is distributed over the face. If the area of interest is away from the stress singularity location, scoping stress results to the area of interest is the way of excluding artificially high stress from the particular result. Now let's see the stress in the sharp corner. Recall from our lesson that geometry discontinuity, like a re-entrant sharp corner, can cause artificially high stress. Click on the solution in the tree. Click on Face Selection Filter. Select these two faces. Right mouse click, insert stress equivalent stress. Right mouse click, evaluate all results. Zoom in to show the max stress in the sharp corner. Recall from the lesson, as the mesh size is reduced, the strains and stresses in the sharp corner will tend towards infinity. Let's now see how the inappropriate boundary condition could cause stress singularity in the model. Click on the solution in the tree. Click on the face selection filter. Select three faces where the fixed support's applied. Right mouse click, insert stress equivalent stress. Right mouse click, evaluate all results. Zoom in to the area of max stress. As you can see, the artificially high stress developed due to the fixed support that we used to connect the wall and the hook. The high stress developed at just one node at the back edge of the hook. Is the fixed support an accurate representation of the boundary? Let's now create a new system on the project page to correct the sources of artificially high stress. Go to the project page, click on the down arrow of System Original, duplicate System Original, rename the new system to Corrected. First, we will address the sharp re-entrant corners. In Space Claim, the fillets will be added to the sharp corners, so the stress will be distributed over the fillet region. Right mouse click on Geometry of the System Corrected. Edit Geometry in Space Claim. In Space Claim, click on Pull. Select the first sharp corner and pull it up. Select the fillet to modify the dimension. Change the radius to 0.5 millimeters. Select Pull. Select the other sharp corner, pull up, select the fillet area and set the radius to 0.5 millimeters. Close Space Claim. Go back to the project page, double-click on the model of the system corrected, click Yes to reread the upstream data. Mechanical is asking if the geometry should be updated since we added fillets in Space Claim. In Mechanical, click on the mesh. Click on Face Sizing. In the Details view, click on one face that was previously selected. Apply Cancel will show up. Click on Face Selection Filter. Select these 5 faces. We would like to have a finer mesh on these faces since we would be interested in getting more accurate stress results on them. Click Apply in the Details view. Element size stays at the same 0.5 millimeters. Right mouse click on Mesh, Generate Mesh. Next we will address the point load. Instead of applying the force on one vertex, the force will be distributed over the selected face, which will give us more realistic stress results. Click on the force in the tree to change the geometry scoping from one vertex to the face. In the Details view, click on one vertex. Apply Cancel will show up. Click on the Face Selection filter. Select this face. In the Details view under Geometry, click Apply. The direction and the magnitude of the force won't change. Next, let's see how we would constrain the model to represent the boundary more realistically and to prevent artificially high stresses from developing where fixed support was initially applied. Recall that the hook is attached to the wall using the screw. Also, the back vertical face of the hook is pushing on the back wall. Cylindrical support will be used to simulate the effect of the screw shank, preventing the hook to move in the radial direction, while tangential and axial directions are free. Right mouse click on Fix Support in the tree and delete. Click Static Structural in the tree. Click on the Face Selection filter. Select the cylindrical face. Right mouse click Insert Cylindrical Support. In the Details view, set radial to fixed, axial and tangential to free. Next, to simulate the compression between the hook and the wall to which it's attached, and the compression of the screw head to the hook's front face, elastic support will be used. The elastic support allows faces to move or deform according to an underlying spring-like behavior. The elastic support is based on the foundation stiffness set in the Details view, which is defined as the pressure required to produce a unit normal deflection of the foundation. Click on Face Selection filter. Select these two faces. Right mouse click Insert Elastic Support. In the Details view, set the foundation stiffness to 10,000 newtons per millimeter cubed. This value could come from experimental measurements or hand calculations knowing the underlying elastic behavior of the materials. Of course, one could also model the screw and the wall and include contact between the parts, but that's not the focus of this lesson. Let's solve the model. Right mouse click on Solution, Solve. Since this is a duplicate system from the original system, some of the results are already in the tree. The equivalent stress shows maximum stress in the fillet. Total deformation shows similar results to the previous case as expected. In this case, we applied force distributed over the area of the tip of the hook, and you can see that the stress location and stress magnitude change compared to the point load case. This represents a more realistic stress distribution. Click on the solution in the tree. Click on the Face Selection filter. Select this face. Right mouse click Insert Stress, Equivalent Stress. Right mouse click Evaluate All Results. This face is away from the artificially high stress area, so the stress result is similar between original and corrected cases. Click on the solution in the tree. Click on Face Selection Filter. Select these three faces. Right mouse click Insert Stress, Equivalent Stress. Right mouse click Evaluate All Results. The high stress shown in the fillet. Although it may look like an artificially high stress, it's not. A mesh study can show that mesh refinement will not cause stress to rise indefinitely or infinitely in the case of the hook with the fillet compared to the case of the sharp corner. This graph shows stress versus the number of elements for the hook geometry with the fillet and without the fillet. You can see that the stress becomes stable with mesh refinement in the case of the fillet, while in the case of the sharp corner stress, it's increasing with mesh refinement. Also, if we look at the stress contours, you can see that the stress is distributed over the area of the fillet, while in the case of the sharp corner stress, is high at just a few nodes along the sharp edge. Similar studies can be done for other areas of the model, such as point load location and the location of the constraints, to check how the stress is behaving with the mesh refinement. This completes the workshop, so let's summarize. In this lesson, we saw when and why artificially high stresses arise in structural finite element models. We saw that the typical cases of these are from point loads, constraints, re-entrant corners, over-constraint of the model, and sharp corners in contact. While the examples we discussed may not cover every case of artificially high stresses we will ever encounter, knowing to look out for these and how to address them will better equip us to use our simulation tools and results properly. We also discussed that there are legitimate cases of high stress, such as stress risers and stress concentrations, where the stress should not be ignored. Examples such as a hole in the plate or a stepped shaft with a fillet. These are not to be confused with the stress singularities we might see in the case of a re-entrant corner. I hope you found this video informative. Thank you for watching, and do check out our other courses to discover more useful learning resources.